Welcome to this video. This is video number 5 in my series of videos on Whitehead and Russell's Principia Mathematica. In this video, I'll be covering the contents of section 10 and section 11 from the first edition of Principia Mathematica, and it would seem natural to assume that we'll just continue here from where we left off at the end of section 9 in the previous video, and in a way that is what we'll do. At least we'll retain the approach that we took in section 9 to a certain extent. But in section 10, we don't merely continue things from where section 9 left off. We'll actually open up another possible approach with which to continue the development of the theory, and effectively we'll have two different possible approaches by which we can proceed. Recall that in section 9 we had two new primitive ideas which we called phi x always and phi x sometimes. And alongside these we had a number of new primitive propositions, and we went on to show that with some appropriate definitions we could prove analogues of the primitive propositions from section 1, which were concerning elementary propositions, and that these analogous propositions were concerning first order propositions. And the upshot was that the propositions from section 2 to section 5, originally proved for elementary propositions, are formally identical for all types of propositions. And the main sticking point that triggered all of this was the realization that the logical symbols, such as negation and disjunction, amongst others, had different meanings depending on the types of propositions that they are applied to. So we took the decision in section 9 to define negation and disjunction as applied to first order propositions in terms of negation and disjunction as applied to elementary propositions. But this is not the only possible approach available to us. Instead of defining negation and disjunction of first order propositions, we could instead take negation and disjunction as applied to first order propositions as well as elementary propositions as primitive ideas. And in fact, we could take negation and disjunction as applied to any propositions of any type as primitive. In other words, we assume as primitive the ideas that the symbols for negation and disjunction have an infinite number of meanings depending on the types of propositions to which they are applied. And this is not to suggest that we're ignoring the problem of different meanings, but simply that we take the different meanings as primitive ideas. So here's how we do this. In section 10, we'll introduce the possibility of taking all of the propositions from section 1 as primitive, but rather than them just applying to elementary propositions, that they actually apply to propositions of all orders. In addition to this, we will take phi x always as a primitive idea, and define phi x sometimes in terms of phi x always. We'll need to take another couple of primitive propositions to allow us to manipulate our expressions in the way that we want to, and basically off we go. The propositions from section 2 to section 5 will immediately be formally identical for first order propositions. However, we don't discard what has been proved in section 9, but we do change tracks to a certain extent. And we do, however, leave open the possibility of using either the approach from section 9 or section 10 once we reach the end of this section. And everything that's proved in section 10 can be proved using either the approach from section 9 or the approach from section 10. It would seem then that section 9 was not really needed, because we could have just taken this new approach, the approach that we begin in section 10, in the first place. Because under the alternative assumptions of section 10, which we could have taken at the start of section 9, we start basically at the point where we finished in section 9. And this is a valid point, but the point of section 9 was to show that it is actually possible to extend the definitions of negation and disjunction through definitions of their meanings as applied to first order propositions. Whitehead and Russell say at the start of section 9 that the purpose and interest of the present number, that is section 9, are purely philosophical. And it turns out that even though we get a bit of a head start in section 10, some of the propositions which we have to give quite lengthy demonstrations for in section 10 using the approach of section 10 are actually much easier to prove using the approach of section 9. So there are pros and cons to both approaches. We get the head start with the new approach, but the old approach does eventually start to catch up. And ultimately, once we get to the end of section 10, either approach from section 9 or section 10 can be used moving forward. Further development of the theory is basically indifferent to the specific approach that we have in mind. Now, whereas in section 9 we were almost exclusively concerned with proving the analogues for section 1 for first order propositions with just a few preliminary propositions proved, in section 10 we're much more concerned with proving propositions involving formal implications. We've actually already come across formal implications in section 9, but formal implication wasn't the main focus of the section. Moving forward, there are two types of implication that we need to consider. On the one hand, we've got material implication, and on the other hand, we've got formal implication. So an example of a material implication is something like Socrates is a man implies Socrates is mortal, or grass is green implies the earth is the center of the solar system. Obviously, our implication doesn't have to be true. All of the propositions from section 1 to section 5 which involved implication involved material implications. And a material implication is an implication of the form phi x implies psi x. Formal implication, on the other hand, are of a different form. They're of the following form. Phi x implies psi x always. So I'll just take a few minutes to explain the importance of formal implications. Formal implications, loosely speaking, can be thought of as a kind of class, in an imprecise sense at this stage, a class of material implications. Both material and formal implications will often just be referred to as implications, and whether it's material or formal implication that's meant is really determined by the context. But formal implications to a certain extent allow us to unrestrict a variable. So we had in section 9 a primitive proposition, 9.14, which will also appear as a primitive proposition in section 10 as well, that says that a propositional function is significant on the whole of a type. But we can, however, restrict our attention to a certain part of a type if we wish to do so. In other words, although the propositional function has a natural kind of range of significance extending over the whole of the type, we can, if we want to do so, restrict to a smaller part of the type. In the same way that if we take something like f of x equals x squared, I could consider this function on the domain x is greater than 0. Even though the natural, let's say the natural domain of this function is x is a real number. So let's have a look at how we can effectively use formal implication to unrestrict a variable. So I'll just take a few minutes to explain how this works. So let's consider the proposition psi x is true when phi x is true. So this has been asserted, so that means that whichever values of x make phi x true, they also make psi x true as well. So just to be clear, this is the propositional function that we're considering, and this is merely a restriction to that propositional function. This is not part of the function itself. In the same way that with the example that I just gave with f of x equals x squared, where x is greater than 0, the f of x equals x squared is the function. Where x is greater than 0 is just a restriction that has been imposed on that function, but is not part of the function itself. So similarly, this is a restriction that's imposed on the function but is not part of the function itself. This is a really cumbersome way of writing things. Not only that, it's not really easy to express this in a purely symbolic form, at least not using the notation that we have available to us right now. What we would like is to be able to reduce this to a much more symbolic form, and also what we would like to do is to unrestrict the variable x. Okay, so the way that we do that is we create another function that effectively involves phi x, or the restriction, as part of the function. So here, the when phi x is true is a restriction. It's separate from this function, but now we're going to try to find a way to bring it in to make a new function where psi x and the restriction on psi x are both parts of the function. So we do this in the following way. we construct the propositional function phi x implies psi x. Okay, so now there's a couple of cases that we need to consider relating to this. Either phi x is going to be true or phi x is going to be false. Well, let's think about when phi x is true. Well, when phi x is true, that means that we're considering a value of x that is not only valid in this function, but it's also a value of x that I'd be happy to put into psi in this proposition here. Okay, so if phi x is true, then the hypothesis of this implication is true, but the implication is also going to be true. How do I know? Well, because this is an assertion. So this tells me that when phi x is true, whichever value of x that I choose that makes phi x true, also makes psi true. So true implies true. The implication must be true. So in the case where I consider values of x that are valid in this function and here, I get that the hypothesis and the implication are both true. But now there's nothing saying here that I can't consider the possibility that phi x is false. Well, if phi x is false, then it seems that I'm considering a value of x here that's valid here, but that is not valid here, because I've excluded the values of x that I put into psi. The values of x that make phi false, I don't even consider putting into psi. So the values of x that make phi false, the hypothesis false here, seem to be the values of x that I've excluded from up here. So in that case, I get a false hypothesis, but I still get a true implication, because even if the hypothesis of an implication is false, then the implication will still be true. And this is important. It seems then that irrespective of whether I choose a value of x that makes phi true or false, the implication is always true. So, therefore, I can form this proposition. Phi x implies psi x always. This implication is always true. But it turns out that the only time that I get both hypothesis and implication true are for values of x that are also possible values of x here. But there is no reason here why I can't consider those values of x that make phi false. And also notice that there is an overlap of the range of significance of phi and psi. It wouldn't be possible for phi and psi to have different ranges of significance, because if I found a value of x that made phi true, but wasn't in the range of significance for psi, then this would just be a meaningless proposition. I certainly wouldn't be able to assert it. So that the ranges of significance of psi and phi must coincide. They must have coinciding ranges of significance. So there's no reason why I can't put the values of x that make phi false. There's no reason why I can't put them into psi. It's just I don't want to consider them here. But here I can. I open up the whole range of possibilities, irrespective of whether x is a value that makes phi true or whether it makes phi false. So I've genuinely unrestricted my variable, and there is a very clear distinction between the two different behaviors that I see here and what's going on here. So here I will only get hypothesis, implication both true when I'm considering values of x that are valid here. But here I will get hypothesis false, implication true whenever I'm considering a value of x that's valid here but is not valid here. So it seems then that formal implication is an appropriate substitute for propositions such as this, where we've got these restrictions here that are initially seem difficult to reduce to a purely symbolic form. Now, we're not saying that the formal implication is an exact symbolic representation of this proposition. It's just that there There are certain behaviours that the formal implication exhibits for certain values of x that coincide with the values of x that are significant in this proposition. And there are certain other values, other behaviours that the formal implication exhibits that correspond to values of x that are not valid in this proposition here. So we're not saying that the formal implication is a purely symbolic representation of this proposition. It's just that it's an appropriate substitute. What we might ask now is formal implication the only way that we can, the only type of expression that we could substitute this for? Are there any other possibilities? Is formal implication the most straightforward, the most efficient way of going about it? And there are other possibilities that we might consider. So we might have something like, I don't know, let's consider phi x and psi x. And, okay, so let's say I try to substitute this with this assertion here. So just to, I'm going to be saying more about the scope of an apparent variable in a few minutes later in this video, but suffice it to say that the scope of the apparent variable here is all of phi x and psi x. Well, for this to be true, what I would have to say is that all values of phi x and psi x are true always. That means that phi x has to be true and psi x has to be true. Well, okay, but if phi x is true, if phi x is true on the whole of the type, then this restriction would effectively be superfluous. The purpose really of this restriction is for it to be meaningful, really. It would be if there were values of x that actually made phi x false. Because remember that phi x and psi x have an overlapping range of significance, so if all of the values of x make phi true, then all values of x are going to make psi true. So this doesn't really result in any restriction. Now I could say phi x and psi x always where phi x is true, but then how is that any better than what I've done here? So this doesn't seem to be an appropriate substitution. Let's consider another possibility. So let's have a look at the expression psi x and phi x, psi x always and phi x. This looks very similar to what I wrote previously, but it's the main difference is the scope of the apparent variable. I will be talking about scope in a few minutes, but suffice it to say that the scope of this apparent variable is just the psi x, not the psi x and phi x. Also, even though I'm using x here as the variable for the psi and x here for the variable of the phi, these variables have nothing to do with each other. For a start off, this is an apparent variable, the x here. The x here is a real variable. So they have nothing to do with each other. This might seem a little bit strange that I'm using the same letter for different variables that have nothing to do with each other, but this is quite a common feature in the notation in Principia Mathematica. And it might seem strange initially, but it becomes quite easy to distinguish within a particular expression. Even though you might have several x's, you can distinguish the x's that are representing different variables, genuinely different variables, and it's actually not too difficult to do that. But if I wanted to try to make things a little bit easier to understand, I guess at this stage, I could write y in there. The reason I'm not going to make a habit of doing this is because in Principia Mathematica Whitehead and Russell don't make a habit of necessarily distinguishing different variables using different letters. Whether a variable is different to another variable really depends on you reading the context properly. That's all there is to it, really. So what does this say? Well, this bit here is saying that psi y is true always, or psi y always. So that's saying that psi is true for every value in its range of significance. That's the unrestricted range of significance. So if I know that psi is true for all values in its range of significance, why would I need to restrict to some of its values? Some values in its range of significance. And the answer to that is, well, I might just want to. In the same way that I might want to restrict f of x equals x squared to just those values of x that are greater than 0. Why would I want to do that? Depends on all kinds of things. I might just feel like doing it, or there might be a good contextual reason for me doing that. Okay, so let's just assume then that this restriction is necessary. Does this do that? Does this suffice? Well, not really. Because, yes, this would require that psi be true for every value in its range of significance, but also it would kind of require phi to be true for every value in its range of significance. So remember the range of significance of phi and psi are the same. They coincide. So I'm effectively saying that psi is true for every value in its range of significance, but also phi will need to be true for every... I'm not saying that phi is true for all values in its range of significance through this proposition, but that would be a requirement for this proposition to be true and for it to be asserted. In which case there is no real restriction here. It doesn't correspond to any genuine restriction, so this doesn't really do what I want it to do here. So unfortunately, the possibilities that we've considered, the alternative possibilities, neither of them really work adequately. So formal implication seems to be an appropriate way to express, or an appropriate substitution for such a proposition as this. And it also seems to be one of the simplest ways. Whether there's a simpler one, I don't know. There might be, but formal implication is simple enough in and of itself, so that's the one that we're going to go forward with. As well as formal implication, we've also got an idea and a notion of formal equivalence. So we've already come across equivalence of propositions in section 4. So now if we've got phi x is equivalent to psi x always, then this is formal equivalence. Actually, I don't need the brackets around it. I could just write that. So this means one way to interpret this is phi x is formally equivalent to psi x. So that's how we would say this. Phi x is formally equivalent to psi x. Only in the case where phi x and psi x are true on exactly the same values of x and false on exactly the same values of x. So that's what we mean by formal equivalence. So I'm just going to take a few minutes now to talk about the scope of an apparent variable. I'm not going to spend too much time on this. There were plenty of opportunities for the scope of an apparent variable to be seen in practice, seen in action as we go through, certainly through some of the propositions from this section. But I'll just have a quick word about it. So if I take the two expressions, phi x implies psi x, so phi x implies psi x always, and I could also take something like phi x or psi x. Okay, so in the first case, the scope of the apparent variable is this here. So it's the function really over which the apparent variable extends. So the part of the expression over which the apparent variable extends. In contrast to this here, the apparent variable only extends over this part of the expression. And this is really indicated by the dots. So in the second case, this dot here serves to kind of bracket off this part of the expression. This dot here serves to bracket off this part of the expression. This dot here between the apparent variable and the propositional function is not a bracket. It does serve a purpose. It tells you it's relating to the scope of the apparent variable. So what I do is I go forward in the expression until I come to either an equal number of dots or a greater number of dots, and then the scope finishes. So I go forward because I've got one dot here. I go forward, oh, I've got one dot there. So my scope will finish here. So in other words, the scope only extends over the phi x here. But whereas in this case, as I go forward in the expression, there are no dots. No dots to stop this. So I get to the end of the expression, and only then do I need to stop. It doesn't matter whether I've got an apparent variable of this variety or of this variety, it works in exactly the same way. So if I take something like a similar expression to this, phi x implies psi x, sometimes I get the same thing. The scope of this apparent variable is the whole of this function. So in these two, I could almost imagine the phi x implies psi x to be replaced by a single function, let's say chi x. And I could replace this with something, I can imagine this being something of this form. Whereas I can't imagine this being of this form. The x here and the x here are two different variables. They've got nothing to do with each other. They're independent for all intents and purposes. This is an apparent variable. This is a real variable. They've got nothing to do with each other. I could change this to these two to a y, which would make it seemingly more clear, but the context is sufficient for me to determine that these variables have nothing to do with each other. And that's important. Even though I use the same symbol to represent different variables, the context clarifies everything sufficiently well. It might take a little bit of practice to start with, but it becomes clear. So the scope of an apparent variable, whether it's of this kind or this kind, is the part of the proposition, expression, or whatever, over which the apparent variable extends. And that's it's effectively what we mean by the scope of an apparent variable. There's going to be plenty of opportunities to see apparent variables in action. The scope of an apparent variable is very important when it comes to distinguishing between formal and material implications. So this would be a formal implication, whereas if I went to something like this, that would be a material implication. Even though I've got apparent variables involved, the apparent variable doesn't extend over the implication symbol. And for that reason, this would be a material implication, whereas this would be a formal implication. So the main theme of section 10 is to take the propositions from sections 2 to section 5, which involved material implications, and extends these propositions as much as possible to propositions relating to formal implication. We're going to accept the primitive propositions from section 1 as primitive propositions in section 10, and that these primitive propositions from section 1 are not only valid for elementary propositions, but they are formally valid for all types of propositions. So what we see then is that we can immediately apply the results from section 2 to section 5 to propositions of the first order, but we can't quite without some primitive propositions in addition to these ones, we can't quite do everything that we need to be able to do. So our new primitive propositions are going to fill in some of the gaps that we need filled in this respect. So in section 10 we take phi x always as a new primitive idea, but we don't in this alternative approach take phi x sometimes as primitive. Like we did in section 9, we took phi x always and phi x sometimes as both as primitive. Here in this alternative approach, we're going to take phi x always as primitive, but we're going to define phi x sometimes, and that's definition 10.01. Notice that phi x sometimes is defined in terms of phi x always, but it also uses negation as applied to a first order proposition. So this is using the fact that we're taking the primitive ideas and primitive propositions from section 1 and now assuming them as being applicable to propositions of all orders. In particular, negation is valid now. It makes sense, its meaning is determined as applied to first order propositions, and therefore this use of negation here is justified. The next two definitions, 10.02 and 10.03, are really relating to, they're just giving alternative notations for formal implication and formal equivalence. So rather than writing formal equivalence as phi x implies psi x always, with the apparent variable here right at the beginning of the expression, we're just going to write the x as a little subscript here next to the right hand side of the implication symbol. And we're going to see both of these notes when it comes to formal implication. We will continue to use both of these notations. We won't exclusively use one or the other. We will see both of them. Similarly for formal equivalence, we're going to see both notations being used, and it really depends on the context and which is going to be easiest for us. So we have these alternative notations, but it doesn't necessarily mean that these are going to be easier to use or more convenient to use in all contexts. Sometimes they will, sometimes they won't. And then we move on to our primitive propositions. So I'm not going to do them necessarily in order. I'm going to pick on 10.11, 10.121 and 10.122. These were also primitive propositions in section 9. In particular, they were primitive propositions 9.13, 14 and 15. And any comments that I made regarding those primitive propositions in section 9 apply equally well here. But 10.11 effectively allows us to go from elementary propositions, to pass from elementary propositions to first order propositions. It's one of the more important primitive propositions, although arguably they're all important. 10.1 it was not a primitive proposition in section 9, it was something that was proved. But here we take it as a primitive proposition. And again, this allows us to pass from first order propositions to elementary propositions. So that's primitive proposition 10.1. Again, the comments that I made regarding 9.2 in the previous video when I did section 9 apply equally well to this. The only primitive proposition that I've decided to write out in full is this 10.12. Actually, this did appear in section 9 as well. It was proposition 9.25. It was proved in section 9. So it wasn't a primitive proposition, although it's very similar to one of the definitions that was given in section 9. I can't remember exactly which definition, but it was amongst the initial set of definitions that we gave, defining disjunction of first order propositions in terms of disjunction as applied to elementary propositions. Now, the reason that I've written this down here is not only to emphasize that the disjunctions here have different meanings depending on what they're being applied to, but also we can see that the scope of the apparent variable is being manipulated here. And this is one of the things that one of the gaps that I was talking earlier on about. We need some gaps filled in with these primitive propositions. We've already got some, but this is another one. We need to be able to manipulate the scope of an apparent variable from time to time. And this is the primitive proposition that's going to allow us to do that. A lot of the propositions that are proved in section 10 are related to manipulation of scope of apparent variables. And this is the one that really gives us our foot in the door, really, in that respect. So we can see here that the scope of the apparent variable is the whole of the expression. Whereas here, the scope of the apparent variable is just the propositional function here, phi x. Arguably, the interpretation of this would be the same in section 10 and in section 9, but I think there's slightly different emphases. In section 9, the emphasis on this particular proposition was more to do with the meanings of the disjunction, showing that disjunction as applied to first order propositions could be defined in terms of elementary, disjunction as applied to elementary propositions. The scope of an apparent variable, it was still there. We could still interpret it in the same way in section 9 as also a way of manipulating the scope of an apparent variable. But here I think it's much more prominent. The issue surrounding different meanings of disjunction is not really an issue for us here. It's more, I interpret this as more relating to manipulating the scope of the apparent variable. So now that we've gone through the primitive propositions from section 10, I've just picked out a few propositions from section 10 that I find most interesting. I'm just going to quickly make some comments on. In addition to the propositions that I'm going to mention, which there's 6 or 7, yeah, 1, 2, 3, 4, 5, 7 propositions that I'm going to quickly run through. There are many more that I'm not going to be able to go through. There's just so many propositions, but really these are just to give a bit of an idea about the kinds of things that happen in section 10. And I won't be going through the proofs or the demonstrations of these propositions either. So the first one is 10.22. I've included this one because it shows how the scope of an apparent variable can change. So on the left hand side, the scope of this apparent variable is the logical product of phi x and psi x. On the right hand side, the scope of this apparent variable is just the phi x, and here the scope of this apparent variable is just the psi x. Even though I'm using x in all of the apparent variables, there's no specific need for me to do that. That's not to suggest that the apparent variables have anything to do with each other. They are, for all intents and purposes, independent of each other. So I could change these two x's to y's and these two x's to z's, and I'd still get a proposition that would be exactly the same in nature. There would be no difference in how I would interpret it. 10.24 was a primitive proposition in section 9. It was the primitive proposition relating to existence theorems. So I made some comments about that in section 9, so I'm not going to repeat the comments. Everything that I said there, it applies equally well here. So, but it suffices to say that this requires demonstration in section 10, whereas in section 9 we just took this as a primitive proposition. 10.25 says that phi x always implies phi x sometimes. I made comments in the previous video number 4, about sometimes how we can take things for granted as we're proving something in mathematics, for example. Sometimes we can take things like that for granted, that if something is always true, then it must sometimes be true, or if it's always true, then it must be true in a particular case. These are very obvious things to us, but we have to understand that our system doesn't automatically have these notions. We need to make sure, we need to put the time and put the work in to make sure that our system has these notions there available to us if we want it to have them. So this is something that does require demonstration in our system. 10.27, again, I've included this because it's an important proposition for a start off, but it also shows how the apparent variable can change scope. So the left hand side, the scope is phi z implies psi z of this apparent variable. The scope of the apparent variable here is phi z, and the scope of this one is psi z. So this is a formal implication. So what we're getting here is that this formal implication implies this material implication. So we have to realise that there is a distinction between the different implications that are involved in this. So we've got the main implication here, which is this one, and then we've got effectively two kind of subordinate implications. This implication here is a formal implication, this is a material implication. And the main implication as well is also a material implication. This was also proved in section 9, this was 9.21, and the demonstration in section 9 was actually much longer than the demonstration that's given in section 10. It's quite unusual that actually, because usually it's the other way around, that demonstrations that run along the same lines as along the lines of the primitive propositions and things like that given in section 9 are usually much shorter than in section 10, but not in this case. 10.271, similar to 10.27, except instead of formal implication here we've got formal equivalence. But again we see a similar effect with the scope. The scope of the apparent variable is changing from one side to the other. 10.3 is the syllogism. So if we've got phi x implies psi x always, and psi x implies chi x always, then phi x implies chi x always. So this is the syllogism as applied to formal implication. And then 10.301, we've got effectively showing that formal equivalence is transitive. You could argue that this is showing that formal implication is transitive, but this would definitely be interpreted as formal equivalence is a transitive operation, or a transitive function. As we go through section 10, there are a few instances of propositions being proved in two separate and different ways. So we could take, for example, 10.23. There are two separate demonstrations given in section 10 for proposition 10.23. The first demonstration runs along the lines of the approach that we had in section 9. And the second demonstration runs along the lines of the approach that we have in section 10, so the alternative approach. So what we see this happening quite often as we go through section 10. What this is showing is that we're not discarding what's happened in section 9, the theory that we've developed in section 9. We're not saying that the approach in section 10 is superior to that of section 9 and that we discard section 9. But we allow the theories, the two approaches, to run alongside each other in parallel. It's just that from time to time, the propositions might need to be proved in slightly different ways, depending on which approach we feel that we're going to take. So ultimately what we get to is, once we reach the end of section 10, we get to a point where everything could be proved using section 9, the approach from section 9, or everything could be proved using the approach from section 10. From that point forward, section 11 onwards, really it doesn't make any difference which approach we have in mind. We just choose our preferred approach, section 9 or section 10, and we can go forward and be confident that everything that can be proved in one system can be proved in the other as well. So they're effectively equivalent systems. Also, something else that I just want to comment on is a particular sequence of propositions that's used in demonstrations in section 10 and moving forward actually. So if we start with something like P implies phi of x. So I'm not saying that this is the exact proposition that we will come across in demonstrations, but something maybe of this form. Then what we can do is we can use 10.11 to assert that P implies phi x always. So P might be a very complex expression in itself. So it's just the form of the expression that we're looking at here. And then I can use start 10.21, which I didn't mention here, but the effect of using 10.21 would be that we end up with P implies phi x always. So we can introduce an apparent variable using 10.11, and then we can change the scope of the apparent variable from the whole of P implies phi x to just the phi x if we want to. There's all kinds of variations on this as well, so sometimes it might be that rather than having P implies phi x always, I end up with P implies phi x sometimes, and I can do a similar thing with that. The specific propositions that I use will be slightly different, but the idea will go along the same kind of lines. So this is a very common sequence of propositions that's used in demonstrations in section 10 and onwards. So that brings us to the end of section 10. So as I've already said, really, once we get to this point, then we can see that either the approach from section 9 or the approach from section 10 are both equally possible, equally valid moving forwards. So we won't really necessarily settle on a particular approach as we move forward, because it really doesn't make any difference. It's indifferent really with what comes up next. So let's move on to section 11, where we move on to the theory of two apparent variables. So here we come to section 11, and this section extends the theory that we've just finished in section 10 to more than one apparent variable. So we're going to mostly be interested in two apparent variables, but we can extend in a fairly obvious way to three or more apparent variables if we need to, although very seldom will we extend beyond three apparent variables. In fact, we'll hardly ever go to three apparent variables. Having said that, there's not a great deal for me to say in this section. A lot of the propositions are effectively two variable analogues of the propositions from section 10. There are a few exceptions to that, which I'm going to make some brief comments on some of the slightly more interesting propositions, but for the most part I'm actually going to be skimming over a lot of the propositions from this section. We kick off with a few definitions really. There's only one new primitive proposition that we'll introduce in this particular section. We start off with a few definitions. 11.01 and 11.02 are relating to the always, extending the idea of always to two apparent variables. 11.03, 11.04, the idea of sometimes to two and three apparent variables. 11.05 is relating to formal implication as applied to two apparent variables. 11.06, formal equivalence as applied to two apparent variables. Because we've started off with definitions here and not primitive ideas, that suggests really that what we have, the theory that we have so far from either section 9 or section 10, is actually sufficient in many ways. It's almost completely sufficient for what we want to do in section 11. The only thing that prevents us from doing everything that we want to do in section 11 is filled in really by, that gap is really filled in by this primitive proposition. But this idea of two apparent variables is not something that's brand new to us. We have actually seen two apparent variables appear in both section 9 and section 10. It's just not much attention was drawn to the fact in either of those sections because it wasn't the main focus. But if we take, for example, proposition 10.22, in the demonstration of 10.22, in the line that's labelled 2 in that proposition, there are actually two apparent variables that appear. And we're able to deal with it. The theories that we have up to that point is sufficient to allow us to deal with two apparent variables. So two apparent variables appeared in section 9 and section 10 in demonstrations of propositions, but if we actually look at the the proposition 10.22 itself, it doesn't include two apparent variables. It's just got one apparent variable. It's just that from time to time in the demonstrations of certain propositions, two apparent variables were necessary to introduce, but then we somehow managed to get rid of them in a certain way. Also, two of the definitions from section 9, definitions 9.0, 7 and 8, I think, involved two apparent variables. So they gave us a way to deal with two apparent variables, even right at the beginning of section 9. It's just they were only used a couple of times, and again in demonstrations. The propositions whose demonstrations they were used in, the propositions themselves didn't have two apparent variables. So there's not really much for me to say about these definitions. They are what they are. I'm just going to say a little bit about this primitive proposition, because it seems to be a little bit obscure at this stage what this means. It doesn't really become apparent what this means until a little bit further on and how this can be used. So 11.07, primitive proposition: whatever possible argument x may be, phi xy is true whatever possible argument y may be, implies the corresponding statement with x and y interchanged. So in other words, this statement here, the first two lines, implies the same statement but with the x and the y interchanged there. Now this can't be reduced to a symbolic form. The importance of this primitive proposition is difficult to appreciate just as it's written here. So I'm just going to give a little bit of an explanation about how this becomes important. It really becomes important when it's used in conjunction with certain other propositions further down the line, particularly proposition 11.11, which is the analogue of 10.11, the two variable analogue of 10.11. So, okay, let's take the statement then. Whatever possible argument x may be, phi xy is true whatever possible argument y may be. That allows me to assert then phi xy. Okay, so let's switch the x and the y around, so I get the statement whatever possible argument y may be, phi xy is true whatever possible argument x may be. What does that allow me to assert? Well, it allows me to assert this. Now, if you notice, they're exactly the same. Phi xy, phi xy. What's the difference? Well, maybe the difference is this primitive proposition I see as really addressing a problem with the notation that's being used, just an inherent defect in the notation. When we see the phi xy, we kind of see the x as the first variable, the y as the second variable, and we see them in that order. What this is saying is that, or the way that I interpret it is, it's saying that there is no real order to the variables involved. Although this is obviously each variable, we can't interchange the variables as such. I can't just change the types of the variables involved, but there is no real order to the variables. It's just a problem that's inherent in the notation, and that's what this is addressing really. That we have two variables, but neither has priority over the other. Neither of the variables is first and the other second. They're just two variables. So if I use, this corresponds to this statement with the x and the y in this order, then 11.11 will allow me to assert xy, phi xy. On the other hand, if I take this statement with the x and the y interchanged, which corresponds to this version over here, using 11.11 in that case, I'm able to assert yx, phi xy. Now that doesn't say that these are equivalent at this stage. It doesn't say that this is the same as this. That's for another proposition, another one that I'm going to mention as we go through. But that just sorts out to a certain extent, at least in my mind, what the significance of this particular proposition is, this primitive proposition. So let's have a look at some of the other propositions now from section 11. So, as with section 10, I've just picked out a few propositions from section 11 that I think are worth highlighting. But like I've already said, for the most part, the propositions from section 11 are effectively analogous to the propositions of section 10, just two variable analogues. So 11.1, this is the two variable analog of 10.1. 11.11, two variable analog of 10.11. We've already seen this when I was explaining the 11.07 primitive proposition. So notice with this one, it says if phi zw is true, whatever possible arguments z and w may be, then xy phi xy is true. The z and the w are in the same order as the z and the w here, but 11.07 allows me to switch the order of these, so I can say if phi zw is true, whatever possible arguments w and z may be, then I get yx phi xy is true. So the use of 11.07 becomes evident as a way to change the order of the apparent variables. So in other words, the order of the apparent variables doesn't have to reflect the order of the variables in the propositional function. We still don't know that those two are going to be equivalent, so xy phi xy and yx phi xy, but that's where 11.2 comes in. It shows that the two are actually equivalent. 11.21 is a kind of a three variable equivalent of 11.2, so here we get a reordering, a permutation by the looks of it of the xyz. So we get effectively the same kind of proposition as 11.2. And then 11.31, I've chosen this one for a couple of reasons. The first is because we can see here, again, as I was commenting in relation to section 10, the scope of the apparent variables is changing. So here the scope of the xy is just the phi xy. Here the scope is the psi xy. Here the scope is the logical products of phi xy and psi xy. But there's also a problem here that I want to comment on regarding the significance of the proposition, of the expressions on either side of this. And this actually applies to section 9 and section 10 as well. We can have a similar problem to what I'm about to talk about. So the problem that I've got in mind is to do with the significance on either side of this equivalence symbol. So let's consider phi, just a reminder about these apparent variables here. Even though I'm using xy here and xy here and xy here, that's not to suggest that they are all the same variables. Okay, so I could change this here to wz psi wz, for instance, replace this with this, and the proposition would be identical. It would be exactly the same proposition, and I could change this to an A and a B, as long as I change both of these to A and B respectively as well. I get exactly the same proposition. So there's no suggestion here that even though I'm using x and y here and x and y here, that this x is the same as this x and this y is the same as this y. And on that note then, that means that the phi and the psi could be functions of different types. Okay? Propositional functions of different types. So that's not a problem on the left-hand side here. I can still form the logical product of this and this, even if phi and psi are different types. What I can't do is form this logical product if phi and psi are of different types. So that means that there is the possibility that if we're a little bit blasé, a little bit careless about how we're going about things, and we choose phi and psi to be functions of different types, then this is fine, but we can't say that this is going to be equivalent to this. we can only say that this is equivalent to this under the conditions that phi and psi are functions of the same type. This is actually a problem as well that we encounter in section 9 and section 10. I didn't talk about it when I was going through section 10. I actually meant to, but I completely forgot about it. But this problem affects certain propositions in sections 9 and section 10 as well. You've got to make sure that the functions are of the same type sometimes to make sure that the whole proposition is actually significant, because we could have the left hand side of this significant but the right hand side not significant, depending on the nature of the functions phi and psi. Okay, so there's not really much else for me to go through with this section 11. There are many other propositions included in this section, but most of them are not particularly interesting in themselves, but they are necessary for, on the one hand, for completeness, but on the other hand, some of the propositions are used further down the line as well. So section 11 is necessary. It's not a very interesting chapter, so I'm going to leave out most of the propositions. I think I've gone through the highlights from this particular section. So on that note, that brings us to the end of section 11 and to the end of this video. In the next video, I'm going to go through sections 12, which is on the axiom of reducibility, and probably section 13, which is on identity. So if you have made it this far with this video, then thank you very much for watching. I very much appreciate it. And I look forward to seeing you in the next video.